here I have the sum of the first n Fibonacci numbers. Now, this is going to be a very interesting video, and I really hope you enjoy it. And thank you so much for over 400 views on my sum of first n natural numbers 3 ways video. I really appreciate the love and support, and so this is a little treat for all of you. So let's review what the Fibonacci sequence is really saying, okay? The Fibonacci sequence is going to be recursively defined, which just means it's defined in terms of previous terms, where f sub n is equal to fn minus 1 plus fn minus 2. It's a very beautiful and famous sequence that appears in all of mathematics and in random events, and so it's been really an amazing piece of puzzling information for mathematicians for centuries. So let's also make sure that we are clear of which terms are defined at, where f0, the initial value, is 0, and f1 is equal to 1. And so if you iteratively plug in these values into fn, you can actually get your values for the sequence where we have fn, okay, like this, where n is going from 0 to big N. This is going to be equal to 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on and so forth until you get to the f big Nth Fibonacci number. So this is the sequence just for you to get a nice visual explanation. And so for some of you who are already really excited to dive into the question right now, I encourage you to pause the video and find out how you can find the sum of the first n Fibonacci numbers by just looking at the sequence alone and deducing any special patterns you might notice, just for those that are especially excited to get into it. But I'll show you my favorite way to find the sum of the first n Fibonacci numbers right now using what's called discrete calculus. But don't be afraid when you hear calculus, because there's actually no calculus involved. First, we got to define a few terms. So I'm going to say discrete calculus. Now, in the simplest of terms, discrete calculus is taking calculus from real numbers to integers, where functions like f of x are now sequences like a sub n, all right, or like fn, like the Fibonacci numbers, okay? And what we're going to do is we're going to define a very important operator on discrete calculus called the forward difference, okay? So forward difference. I'm going to write that out. The forward difference of a sequence a sub n, denoted as delta a at the value of n, all right, at the nth value of a, is defined, so we have a little triangle on top of the equal sign to show definition, as the next term in the sequence minus the current term, okay? And so you might already see a similarity between calculus and discrete calculus in this sense, because when we look at dy dx, all right, the derivative of a function y with respect to x, is defined as the limit of a difference quotient, where it's the limit as delta x goes to 0, okay, of delta y over delta x. And in fact, those deltas are actually a forward difference, because that's going to be a slope of a secant line, all right, where x is going to 0 of yn plus 1 minus yn over xn plus 1 minus xn, all right? That's essentially the connection between the discrete and continuous cases of calculus. All right, now we have this out of the way, we can now turn our heads to a very important result known as the fundamental theorem of discrete calculus. So fundamental theorem of discrete calculus. Now don't be afraid when you hear fundamental theorem of discrete calculus, because I promise you that it's far more simple to prove, and we're going to do that in this video right now, than the actual fundamental theorem of calculus in smooth calculus. So it states that the sum, okay, as the value n goes from red kind of, or in red a, to some final value b, okay, of the forward difference of delta a at n, the sum of those values is going to be equal to the original sequence a at n, where you evaluate the n subscript at, on the top, b plus 1 and the bottom a. And so this is essentially the same thing as saying a sub b plus 1, like this, minus a at big A, like this. And so how would you prove this? I encourage you to pause the video right now using what you know just already about the forward difference and the fundamental theorem of discrete calculus to prove this result. And so I encourage you to pause the video and give yourself some time to do that. It's a very beautiful and very simple proof, almost deceptively simple. So let's prove that, all right? The proof involves writing out the terms by their index, all right? So we're going to write these terms out lengthwise and starting at the top with b, all right? And what we're going to do is write out delta a at b. What's delta a at b? It's going to be ab plus 1 minus ab. So we have ab plus 1 minus ab. And now we're going to go down by 1, all right, with the sigma. And so we get delta A at b minus 1, which is going to be the same thing as saying a sub b minus a sub b minus 1. And then we go another down one, b minus 2, where the delta at b minus 2 is going to be equal to a b minus 1 minus a b minus 2, just using the definition of the forward difference. And we can keep adding terms until we get to, say, a plus 1, where delta a at a plus 1 is going to be a sub big A plus 2 minus a at big A plus 1. And finally, at the last term, delta a at big A is going to be a sub big A plus 1 minus a sub big A. Like this. And basically, you can see some beautiful cancellation. These ABs cancel out, AB minus 1 cancels out, and AB minus 2 will cancel out with its own friend. And essentially, you just keep canceling like this with a bunch of madness, cancel out everything here, until you're left with two terms that don't have any friends to cancel with. You have AB plus 1 and A at A. And that's exactly why the entire sum is called a telescoping sum. It basically telescopes like this into two values, the start and the end. And we get ultimately A sub big B plus 1, all right, minus A at big A. And this is one of my favorite proofs in all of existence. It's just amazing. The telescoping sums are awesome. I encourage you to look at those a bit more. All right, now that we've been armed with just the forward difference and the fundamental theorem of discrete calculus, we can now tackle the problem at hand. Let's consider the forward difference of the Fibonacci numbers, okay? And it's going to be helpful to write out a table here where we have an n value, we have f at n, and then we have delta f at n, okay? Like this, all right? And so let's just kind of split this into a table so we can keep track of values. N equals 0, 1, 2, 3, 4, 5, 6, 7, 8. And so I encourage you to also, as a practice for forward differences and Fibonacci numbers, fill in this table on your own before I do it myself. But let's just get it right into it. 0, 1, 1, 2, 3, 5, 8, 13, and 21. All right, so what's the forward difference? Well, the next minus the current is going to be 1. Next minus current is 0. 2 minus 1 is 1. 3 minus 2 is 1. 5 minus 3 is 2. 8 minus 5 is 3. 13 minus 8 is 5. 21 minus 13 is 8. Wait, hold on a minute. Do you see that? We've found the Fibonacci sequence repeating itself within the forward difference. But not only that, but we've also found that there's a weird 1 here. What does that mean? Well, if f at 0 is equal to 1, then that means that this somehow must be f sub n minus, or f sub negative 1. And indeed it is. And so not only are forward differences amazing in the fundamental theorem of discrete calculus, but also they're absolutely amazing in the fact that you can count backwards in sequences. You've officially counted the Fibonacci sequence backwards, where f sub minus 1 is equal to 1. That's a true fact. So that's really amazing, and that's why I love forward differences so much. So anyways, we found essentially that delta f at n, all right, is basically a right shift, all right, of the sequence. Everything shifts right by 1, which is also expressed as an operator called E, capital E. So it's EF at n. But that's essentially the same thing as saying Fn minus 1, like this. All right? So with this information, we can now build the sum. Is there a way we can express Fn in terms of a forward difference? Well, we can. Watch this. So if we have the sum as n goes from 1 to big N of the Fibonacci sequence at n, like this, which is the question we're trying to solve, we can change the indices. We can re-index, it's called, where we change the bounds on the top, bottom, and the function itself to remain the exact same, but in a way that's more friendly for forward differences. So let me show you how we're going to do that. We have the sum. It's a pretty bad sigma. I'm trying to draw a better one. There you go. Pretty good. All right, that's the same thing as saying n goes from 2 to big N plus 1 of f at n minus 1. And compare that to the original sigma. Plugging in the first value n equals 2, we get f1. And we indeed get f1 when we plug in n equals 1. Plug in the last value, n plus 1, we have f at big N, and so indeed we'd have f at big N. So we know that we've conserved the actual sum. It's the same thing. But in this case, we've just shown that delta f at n is equal to fn minus 1. And so we can now rewrite this as the sum, okay, as n goes from 2 to n plus 1 of f, and not just f, but as delta f now. Delta f at n. There you go. And you might be wondering, why am I starting at n equals 1 instead of 0? But that's also because f sub 0 is actually equal to 0, and so that's not really helpful for us. It's not really interesting to add 0. So anyways, This, by the fundamental theorem of discrete calculus, is going to equal just the Fibonacci sequence evaluated from b plus 1. So if this is b, then b plus 1 will be big N plus 2. And then a is 2, so we just remain at 2. And that's going to be equal to fn plus 2 minus f of 2. And in case you forgot what f of 2 is equal to, it's equal to 1. And so therefore the sum of the first n non-zero Fibonacci numbers is going to be fn plus 2 minus 1. And there you have it, folks. That is exactly what the sum is equal to. So let's go back all the way to the top and put down the answer. So this is equal to fn plus 2 minus 1. And that's an amazing result. And it's such a clean, beautiful result. There's no crazy formulas. You just have to know that you just have to go a couple more sequences forward. So that's really awesome. And so what we're going to do is we're going to actually check if this answer makes sense. All right? Let's suppose our big N is equal to 5. So we're going to add 1 plus 2 plus 3 plus 4 plus 5 terms, which means we're adding 1 plus 1 plus 2 plus 3 plus 5. So 2, 4, and we have 7, 12. So that in theory, the sum should equal 12. And let's see if the formula gives us the same thing. At n equals 7, we have 13. Subtract 1, we get 12. And that's amazing. There you go. It works. So that's just another kind of sanity check in case we were not sure. But there's also an interesting situation where right from the outset, I encouraged you to think about the pattern that could be involved in summing together the first n non-trivial Fibonacci numbers. So this means without a zero. And if you look at the recursion here of the Fibonacci sequence, you see that fn is equal to fn minus 1 plus fn minus 2, which also means that fn minus 2 is equal to fn minus fn minus 1. And guess what? This, by definition, is equal to the forward difference of f at n minus 1. All right? And so right away you could deduce that in general, if fn minus 2 is equal to the forward difference of f at n minus 1, then delta f at n is equal to f at n minus 1. So in theory, you wouldn't even have had to write out a table. You could just see the recursion right away and then apply the fundamental theorem of discrete calculus, or just use a telescoping sum if you weren't aware that the fundamental theorem of discrete calculus existed. So this is just another amazing hidden structure within the recursion itself. So I really hope you appreciated and enjoyed this video, and appreciated the beauty of telescoping sums and of the Fibonacci sequence itself with this special property, where taking the forward difference is essentially just shifting it by 1. Not all functions have this sort of recursion built in them like this. So anyways, I really hope you enjoyed the video. Thanks so much for watching, and stay tuned for the next ones. Till then.